Okay, hello guys, welcome to the discussion of tutorial 3. Let's discuss problem number 1 first. Problem 1. Okay. What is problem 1? Problem 1 is a particle located at a point x naught y naught in Cartesian coordinate system. It's experiencing a potential of function u equal to u naught. Let me write that u equal to u naught into e raised to x square upon a square into sine 2 pi y upon b. This is your quantity, it's a scalar quantity, where u naught, a and b are constants. Find the magnitude and direction of the maximum rate of change of u with position. So how to find out the magnitude and direction of maximum change? So let's say this function is distributed over a space, three-dimensional space, and spread over the area. And how will you find out which area this one is changing for maximum? For example, temperature is it is spread over a room. If you go in which direction the temperature is changing maximum? How to find out that? The method is take the gradient of that function, gradient of this function. This will give you the direction of maximum change, direction also the magnitude of the maximum change. How is this possible? To explain that, let me take a small mathematical digression here. That digression, and I will denote a new scalar function here. That scalar function f is defined as a function of x comma y comma z. Okay, now in our Cartesian coordinate system, let this function is varying in all the direction x, y and z, and I am looking at some direction along this dl. Okay, what will be the dl here? So dl here will be equal to dx x cap plus dy y cap plus dz z cap. This is my dl. Now let's see what is the change df. Df, the change in the total function df. So this I can write as del f upon del x into dx. This is what happening along the x-axis. Then there is del f upon del y into dy. That's along y-axis. Then del f upon del z into dz. This is the total change in the del f. Now using this dl, I can write df again as something like this: del f upon del x into x cap plus y cap into del f upon del y plus z cap into del f upon del z dot dx x cap plus dy y cap plus dz z cap. So if you dot product it, what you get is this one, right? This is just simple mathematics that you can do. Now I am denoting this one with some different notation. Now this is going to be denoted as this one, that is called gradient of f. This as dl. So now what is happening? We have df equal to gradient of f dot dl. So this quantity nabla, this we call nabla, I am defining it as del upon del x into x cap plus del upon del y into y cap plus del upon del z into z cap. This is what you have. This is your nabla operator. This operator, when it is operated on some scalar quantity, we call it as gradient of f. When this nabla operator now it is operating on some vector, we call it as divergent of f. Divergent of the vector. And when it is acting on this vector like this as a cross product, we call it curl of vector v. Okay, so now therefore here in this case what we have, the change in df is a dot product of del f dot dl, gradient of f dot dl. Why are we calling this gradient of f as the maximal change? That is what our discussion is. Now look at this, our function. This function is defined here in this space x and y and z, and now I am saying this is the path I am looking at. Let's say this is the maximal change dfm. Okay, and there is an angle theta it is making. Now I am not looking in the direction of the maximal change in that f. This dfm is the maximum change. Okay, maximum change in f function x comma y comma z that's the dfm. So now I can write it here like this dfm. This df, now I can write this one as magnitude of del f dl cos theta. This is this equation we know. So when will this df will be equal to maximum? Df will be equal to maximum when this one dfm, that is df max I am writing, This will be maximum when I can write this one as simply this one, that is like this, the magnitude of grad of f dot dl, that is theta is equal to 0, which is theta equal to 0 means what? According to the figure you see that dl has to be, that means the direction I am looking at has to be along this direction, that is when this maximum change is happening. So which means if I look along the direction of the gradient of this function, I will get the maximum change, which means this gradient of f has the both magnitude and direction of maximum change. This gradient has the this has both the magnitude and direction of the maximum change. That is the meaning of it. Unless this is the meaning of it, I will not get df maximum when I go along the del f. That is the meaning of it. So we can use this gradient in our discussion. So that is what we are going to do. So to find out this gradient of u, we can now use our definition we obtained from here, that is del f upon del x, del u upon del x along x cap plus del u upon del y along y cap. Why did I wrote only 2? Because this u is only a function of x and y. We already wrote it, our u here is simply a function of x and y alone. So if I differentiate it, what I am getting, this answer is equal to u naught into e raised to x square upon a square into whole into sine 2 pi y upon b into x square 2x upon a square x cap plus 2 pi upon b into cos 2 pi y upon b along y cap. So this is the answer for del gradient of u. Now in the question we have to find the particle is at x naught y naught. Now what is the direction at that point? For to get that point, substitute that value of x naught and y naught. So you will get u naught into e raised to x naught square upon a square into sine of 2 pi y naught upon b into 2x naught upon a square x cap plus 2 pi upon b cos 2 pi y naught upon b into y cap. This is the maximal change at that point. Okay, this is the maximal change at x naught and y naught. This is the answer. So remember this any change in any function, two things you have to remember. Any change in the function can be written as this gradient of function dot dl, and this gradient of function will always have the magnitude and direction of the maximum change of that function. This both you should remember, because these are going to be useful for the discussion of problem 2 and problem 3. Go through this problem again, try to do this yourself, make yourself convinced why the gradient is maximum, the magnitude and direction of the maximum change. Okay, and let me know in the comment section if you have any doubt, or in the team's group discussion. Okay, thank you for watching this video, and we have the problem 2, problem 3 and problem 4 and problem 5 are uploaded, also will be uploaded following this video. Thank you for watching again.